Noise, sir. Sir, please unmute, sir. Master Bhaskar, sir, ఒక్క నిమిషం unmute చేయాలి, sir.
Okay.
Please, okay, sir, done.
Okay. So, hello, Pratap, how are you? So, shall we start?
Okay, sir.
Or anything else is there? Shall we start? Share screen, share.
Good evening, one and all. On the occasion of 103rd birthday anniversary celebrations of Dr. Komroval Chandrasekharan Garu, our Department of Mathematics, Bapatla Engineering College, Bapatla, is conducting a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. On the first day, Dr. N. Sudhakar Garu, Professor, Department of Computer Science, Bapatla Engineering College, Bapatla, delivered a talk on machine learning models. On the second day, Dr. KNVV Prasad Garu, Senior Assistant Professor, Department of Mathematics, Guru Gasta Viswavidyalaya, a Central University, Bilasapur, delivered a talk on the problem of discontinuity at a fixed point. On the third day, Dr. C. Pavan Kumar Garu, Faculty in Mathematics, Apex Maxwell Excel Center, North Carolina, USA, delivered a talk on applications of linear algebra in machine learning. On the same day, in the second session, Dr. N. Padikumar Garu, Professor and Head, Department of Mathematics, Vijnan Institute of Technology and Science, Hyderabad, delivered a talk on Introduction to Mathematical Modeling in Ecology and Epistemology. On the fourth day, that is yesterday, Dr. P. Anuradha Kameswari Garu, Professor, Department of Mathematics, Andhra University, delivered a talk on solving minimal solution of Pell's equation using lattice reduction. For all the above 4 days, each session is engaged with approximately 700 participants. Thank you, one and all, for your good response and valuable support. Today is the final day in the 5-day program, and today's speakers are Dr. J. Bhaskar Bapuji Garu, Professor, Department of Mathematics, Anna University, Chennai, and Dr. D. Pratap Garu, Associate Professor, Department of Mathematics, CMR Institute of Technology, Bangalore. Now I request one of our staff organizers, Ms. I. Rajeswari, to present profound profile of Dr. J. Bhaskar Bapuji Garu.
Good evening all. Welcome you all to a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. I feel it proud to introduce today's resource person and dynamic researcher, Dr. J. Bhaskar Bapuji Garu. Dr. J. Bhaskar Bapuji Garu is a senior professor working in the Department of Applied Sciences and Humanities in Anna University, NIT campus, Chennai. He did his BSc, MSc, and MPhil in mathematics from Madras Christian College, Chennai during 1986 to 92. He got Cambridge University Scholarship, Aberdeen Scholarship, Defense Scholarship while doing MSc at Madras Christian College. He received joint CSIR, UGC, and JRF in the year 1992 in the area of mathematical sciences. He did his PhD in Jawaharlal Nehru Technological University, Hyderabad in the year 2004. He has published 158 research papers in various reputed international and national journals. Out of them, CSI 12, Scopus 45, UGCK 26, Web of Science 3. 14 students obtained PhD and 31 students obtained MPhil under the guidance of Dr. Bhaskar Bapuji Garu, and still guiding from students for PhD at present. He also guided and completed 66 MSc projects to his credit. He is a reviewer for Mathematical Reviews, American Mathematical Society, European Journal of Combinatorics, Southeast Asian Bulletin of Mathematics, and Allahabad Mathematical Society. He delivered 120 invited talks in various international conferences, seminars, and webinars. He got numerous membership in scientific and professional societies. Presently, Dr. Bhaskar Bapuji Garu is working in the areas chemical graph theory, graph labelings number theory, and cryptography, formal languages, and automata theory. Professor J. Bhaskar Bapuji sir is appreciated by one and all with his best way of teaching and remarkable research for the last 3 decades. His friendly nature, good attitude, gentle behavior, research capabilities, or additional qualities in him apart from his goodness and vast experience in the field of education and research.
Thank you, Ms. Rajeswari, for your nice introduction about Dr. J. Bhaskar Bapuji Garu. Now, I hand over the session to Dr. J. Bhaskar Bapuji Garu to deliver his lecture on topological indices of molecular graphs and drug design. Dr. Bhaskar Bapuji, sir, please start the session.
Yeah, thank you, Professor. Can you share the screen now? Is it visible, sir? Is my screen visible? Karnakar, sir?
No, sir. No,
Yes, sir. It's visible.
Visible. Okay.
Visible?
Yes, visible, sir.
Okay. Got the full screen, sir? Got the full screen?
So please share, Babji Garu.
Yeah.
So please share your screen.
Yeah, that I have shared already because you have to share it because I cannot do it.
Okay. 1 minute, sir.
You have the option. Only the
1
meeting
minute.
organizers can present and
Yeah.
share.
Okay, right. Done, sir. Oh, nice. Got it.
The screen has come or it's not come?
You're getting the entire screen, sir. Now it was stopped.
So just open PPT, sir.
Yeah, I've just got the screen now.
Yes, sir.
Full screen, sir.
Got it.
Okay. So good afternoon, one and all. I do join with the organizers, their home team, to welcome all the participants for this beautiful international FDP on application of mathematics in various fields with innovation approach. It will be incomplete if I don't remember the days which I was working in Bapatla Engineering College with all my wonderful friendship and colleagues. I had this position only due to working in Bapatla Engineering College. I should register my sincere thanks to my supervisor, Dr. N. Prabhakar Rao, the former HOD of Max Department, Bapatla Engineering College, who has been my supervisor, and all my friends, TSR, Karnakar, Pratap, and all other people who work with me. So I feel very proud to join with this FDP as a resource person. So let me go to the topic. Maybe few people will already be familiar with this area. chemical graph theory. So let me go to the various parts elementarily and then go and touch for the drug design. How our mathematics, especially graph theory, is going to be used as a fundamental tool for designing drugs. Okay, so this is the topic. So in order to make it easier to the reader to understand the methods, coding, the chemical structures from molecular graphs, some concepts like adjacency matrix, characteristic polynomials, Laplacian matrix, topological indices will be discussed. So the idea is to introduce to you what is called topological indices, which is essentially a numerical molecular descriptor associated with each molecular structure. It's going to be a number, right? So mathematics means numbers. So numbers are attached, like we are attaching a number for a person, like for Aadhaar number. It's a unique number, one-to-one bijective function. Here we don't have such type of uniqueness because chemical compounds are isomorphism and structures may vary, but numbers may not vary, to be same. So that depends. We are going to study about the range of the numbers and discuss a lot of things. So some numerical descriptor is going to be assigned. That's called the topological index. So the broad area of this study is called chemical graph theory. Of course, the importance of algebraic concepts in chemical graph theory will be highlighted to motivate the young researchers who would like to work in this area. As we know that graph theory has a wide range of application in engineering, physical, social, biological, linguistics, various other areas. The graph can be used to represent almost any physical situation involving discrete objects. So once you have 2 points, if they're related, then we can bridge them by an edge or a link or a line. So the relationship and the points or the objects plays a major role. So graph is a 2-component having points and lines. It's called the basic thing, like vertices and edges. Quantitative structure activity relationship and quantitative structure property relationships are the 2 attempts which we are going to do to correlate the activities of the structures of the compounds. Fine. So the most interesting basic concept which we study in our maybe 11th standard or 10th standard textbook, science books, is hydrocarbons. So a compound which has only 2 atoms, hydrogen and carbon, is called hydrocarbons. So hydrocarbons, there are 2 types of hydrocarbons, saturated and unsaturated. When we say saturated, it would satisfy the valence of the carbon atom. The valence is 4. So here, this is saturated. So this carbon atom is linked with this 3 hydrogen and 1 CC bond. So this carbon atom has 3 hydrogen and 1 C bond. So 4 corners are with the atoms. Whereas in this, it is unsaturated because these 2 hydrogen is being plucked out. If you pluck out these 2 hydrogen, then it has to be balanced. To be a stable compound, it itself forms another bond, a double bond. So it's an unsaturated. Similarly, if you pull out these 2 hydrogen again, if it has life still, it will get attached. You get the triple bond C2H2. So saturated and unsaturated hydrocarbons. Fine. So for us, we don't bother in mathematics whether the compound is saturated or unsaturated. We bother only about the link between the atoms. So that I'll come to the next stage. So here, the topological representation of a molecule is called a molecular graph. How do you represent a molecule? So that representation is called a molecular graph. So what we do is we take the vertices of the vertices to be the atoms and the bonds to be the edges. The study is to correlate and predict the physical, chemical, biological properties from the molecular structure. That plays a very important role, and it's an unsolved problem in theoretical and computational chemistry, environmental chemistry, medicinal chemistry, and life sciences and so on. So representing an object giving information about the number is compromised by their connectivity. Well, so that is called topological index. So now look at this molecule. The molecular graph is a collection of points representing atoms in molecules, set of lines representing covalent bonds. This is a propane C3H8, not C2, C3H8 propane molecule. So this is the molecular graph respective to this propane. So for all the atoms are dots, vertices, and the lines are edges. So I remove all the hydrogen. Only think of the carbon-carbon skeleton that is called hydrogen diploid polygons. In our study in hydrocarbons, we are going to remove the hydrogen atoms and we utilize only the CC bonds for our study. So this is methane as carbon in center and hydrogen. So satisfy the balance. Okay. So the idea is to go to the next level with the help of the molecular graph. Okay, polynomials provide both a powerful mathematical tool, a valuable proof technique to certain fields in graph theory. So how we are going to go to the polynomial from a molecular graph? So that we will be studying. Look at this particular compound, 1, 2, 3, 4 carbon butane. The second position you have a methyl and another methyl, so it's a 2,2 dimethyl butane compound. So I will find out the hydrogen diploid molecular graph, which has 6 vertices, 6 carbon atoms and their respective connections bonds. So I am able to draw a molecular graph for me now onwards. This is the graph. Hydrogen diploid molecular graph is my graph. So I take a compound 2,2 dimethyl butane and prepare my graph. This is my graph with 6 vertices. Well, now I will write the adjacency matrix for this particular graph. Adjacency matrix, this is 1, 0 matrix. Whenever there is an edge between two vertices, I will put 1. If there is no edge, then put 0. So here, V1, V2, V3, V4, V5, V6 row, and V1 to V6 column. It's a square matrix with the 6 rows and 6 columns. And if you look at the compound, here, if I take this as V1, V2, V3, V4, V5, V6, there is an edge between V1, V2, V2, V3, V3, V4, V2, V5, V2, V6. So there are only 5 edges here. So if you look at the graph, there are 5 edges in the upper triangle, 5 edges in the lower triangle, symmetric matrix. And there is no self loop. So the principle, the diagonal elements are 0. V1 is connected with V2, so 1 the row, degree of the vertex. V2 is connected with the V3, V4, and V5, V6. V1, V3, V5, V6. So that's 4 ones. So V3, only 1 the row. Like this, you can study this. So each row, number of ones gives it degree. Fine. So this is called adjacency matrix. What we are going to do with this matrix? We are very familiar with the characteristic equation. What is a characteristic equation? Characteristic equation is got from the concept of the eigenvector. So there exists a non-zero column vector x such that if you multiply the matrix A by x, you get lambda x. So this equation gives us the beautiful concept of the eigenvalue lambda, and this is a non-zero vector. So the eigenvalue of the matrix is such that if we could find a non-zero column vector x and Ax gives lambda x, this is called the eigenvalue lambda, that is called the eigenvector. And if you take the left side and give the determinant equate to 0, this is the characteristic equation. This polynomial is characteristic polynomial. Here we get a polynomial of degree 6 because it's a matrix, square matrix of order 6. Fine. So this is called the characteristic equation of the square matrix A. So what we did is we took a compound, we have drawn hydrogen diploid molecular graph, and then we wrote the adjacency matrix. And next we are taking the characteristic equation, determinant A minus lambda equal to 0. So when we solve the characteristic equation, we get values, n values for lambda for n by n matrix. Okay, so later we will see what is the use of this lambda. Now, right now, if you try to write this polynomial in the a different way, you can write determinant of xi minus a, or whatever it is. If it is the characteristic polynomial, the expansion is x power n c g1 x power n minus 1 c g2 x power n minus 2, so on. And if you look at this interesting, the coefficients of the polynomial will give a lot of information of the polynomial, information of the matrix, information of the system. So that's why we say the polynomial is a very powerful tool in mathematics to analyze plenty of things about the function or whatever the polynomial represents. So this is the general way of writing the polynomial. And the question now is that this is 0, the quotient is x power n is 1, and the quotient of each term has a meaning. Okay, so let us come to that. If you look at this particular graph, this just take a structure. We have a cycle, and we have the two cycles, three C3s, right? So two triangles. So to have something interesting here, let us write out the characteristic equation. So determinant of a minus lambda, right, in the determinant of a minus xi. So I get a 4x4 matrix. X power 4 minus 5x square minus 4x. So if you take the coefficient of x cube, it's 0. The coefficient of x square is minus 5, which is a number of edges here. In this particular graph, it is number of edges. Minus of C2 is the number of edges. So minus of minus 5 is number of edges. And quotient C3 by 2, negative of this by 2 is the number of triangles. Okay, this is an observation to just for a motivation to make you think that there's some connection between planar graph, geometry in planar graph, maybe the simple fundamental concepts in planar graph along the coefficients. But the right aim is now is to talk about the coefficient of x cube, and the coefficient constant term is missing. If you look at closely, the coefficient of the x cube term or x power n minus term is always 0. It's always 0 because when you write the adjacency matrix, you can see that the principal diagonal is always 0. So, you know, the trace of the matrix is the sum of the principal diagonal elements, sigma ai. So the trace is 0. Therefore, the coefficient of x cube is always 0. That's one thing which is constant in the polynomial. So general property. And then here the constant term is missing. That means the determinant of the matrix is 0. Therefore, when its determinant of the matrix becomes 0 means at least one eigenvalue becomes 0, because product of eigenvalues is equal to determinant of the matrix. So here, if you take the 4 eigenvalues, definitely one eigenvalue is going to be 0. That is the conclusion. So these are the some types of studies with the algebraic concepts and the structure. So whatever may be the molecular graph, this is the general principle of the polynomial, right? So next, let us slightly go to the interesting part of our graph theory, bipartite graph. It's not complete bipartite, it's a bipartite graph with 5 vertices. And I can construct a 5x5 matrix, adjacency matrix, and the characteristic polynomial. Again, if you look at the characteristic polynomial, it is x power 5 minus 3x cubed plus x. That's all. As I mentioned earlier, the coefficient of x power 4, x power n minus 1 is always 0 because the trace is 0. And here also it seems that constant term is missing. So don't come to conclusion that always constant term is missing. This is for the case of our bipartite graph. This structure is missing. So that means eigenvalue, one eigenvalue at least 0. So let us work out the eigenvalue, look at the eigenvalue. One eigenvalue is 0 and other eigenvalues are in pairs. So this beautiful incident happens only for a bipartite graph. plus or minus 1, plus or minus 2. So they occur in pairs in opposite sign. So if you take the sum of the eigenvalues is 0, product of the eigenvalue is 0. So this is the thing property which we can realize from this particular polynomial. Right. So likewise, I can find the eigenvalues lambda 1, lambda 2 of adjacency matrix. And then I have a, once a mathematician sees something, he goes for a conclusion, right? Some type of a result. Two graphs are said to be isomorphic with their characteristic polynomial coincide, of course, fine. But the converse is not true. So if G and GB are two graphs having equal characteristic polynomial, it's not necessary true that they are to be isomorphic. That is the problem here. So two non-isomorphic graphs can have equal characteristic polynomial. Can you find the compound? So there's two compounds, 2,3-dimethyl pentane and 2-methyl 4-ethyl hexane. So the characteristic polynomial is common. Both has 9 carbon atoms. So this is the characteristic polynomial x power 9 minus 8 x power 7, 19 x power 5, and so on. And this is the compound. The second and third place you have methyl. It is a 2,2-dimethyl pentane. Okay. Heptane should be heptane. Yeah, heptane. HEPTNA, 7 carbon atoms in the stretch and 2 branches. And the next compound is second position a methyl and fourth position an ethyl, C2H5. This is CH3, this is C2H5. So both structures are different. They are non-isomorphic, but their polynomial is equal. So that's a converse case. So we can extend this idea and then we can go for graphs with the different structures having same polynomial. So these are some examples. So we can try out produce a discontented graph. So graph polymers are frequently used in chemical application graph theory. And a few to be mentioned, we can study in literature, plenty of theories are there. Hankel molecular orbital theory relates the simple electron models concerned with the topology of conjugated molecules. The characteristic polynomial of the molecule function in this context as the scalar determinant. Then theory of aromaticity, where we talk about resonance energy and so on. And zeros, the roots of the polynomial. Class theory. So likewise, there are few theories which where is connected with the polynomials. So coefficients and the zeros of the characteristic and the matching polynomials reflect on the skeleton of the molecule. Fine. Okay. So if you go in this way, we can also talk about the zeros. Okay. Need not be all distinct. Okay. So these zeros are denoted by x1, x2, xn. So I can write the polynomial to be like this, not as a real numbers. It can also be complex number. Also, we know this by our experience of handling problems. Sometimes we get a complex, roots. Students used to struggle and get a doubt, get a complex root. Sometimes it happens. And the collection of all even eigenvalues of a graph is called spectrum of the graph. Spectrum of the graph has very important application in theoretical chemistry because it intimates the relationship between the eigenvalues of the molecular graph and Hankel molecular orbital energy levels. See the beauty here. If you take the eigenvalues, lambda 1, lambda 2, lambda n, if you sum the eigenvalues, the sum is going to be 0. That's the trace of the matrix. Suppose you take the absolute value of the eigenvalues, so modulus of lambda 1, modulus of lambda 2, that is sigma modulus lambda, that gives the energy, the molecular graph that we'll see in the later stage. Well, this is a result called Fabregas theorem. The limitations of the graph spectrum is determined by the maximum balance, the Dmax, the graph, and the negative of this. Inequality is achieved in the right-hand side if one of the vertices of the graph have the same valency. Equality achieved on the left-hand side if the graph is a bipartite graph. So non-isomorphic graphs may possess identical characteristic polynomial, hence ideal spectrum. So everywhere mathematician wants to have a bond, where is the eigenvalue line? The eigenvalue line is lower bound is minus of the maximum and valence and the vertex Dmax. So topological indices based on distances. Another one is topological indices based on connectivity. So two types we can classify. Initially, we had a topological indices based on distances. The old index is the Wiener index. And slowly, all these index are been done before maybe 2000. All the indexes are before 2000. This is the oldest index, 1947 Wiener index. But today, we are crossing all those things. We got about not only connectivity, distance, degree distance both. This is topological indices based on degree of the vertices. The most oldest is the group is Zagreb index. Then later we got Zagreb 1, Zagreb 2, then Zagreb co-indices, modified Zagreb. So plenty of revisions is going on till today. And these are all plenty of indices which has been found to study the physiochemical properties of a chemical compound. I said these are all numbers. This is a number which is related to degree of the vertices. This is the number related to distance between vertices. So two types of calculation will be going in topological indices. One is distance based, another one is degree based. And today we are in combination of both distance and degree. After 2000, plenty of advancement has come in the field. Right? So he's the man behind this concept, 1947, Harold Wiener. Okay, he's the man who found the Platt number, W polarity number. Later, path number was termed as Wiener number. So the topological index is a numerical parameter of a molecule based on certain features corresponding to graph. It's an invariant number, the molecular structure. Okay, Wiener, he predicted the boiling point of hydrocarbons by a linear formula. That is, the boiling point TB of an alkane is AW plus BP plus C. So as I mentioned, alkanes, alkenes. Earlier I was talking about saturated, unsaturated. Saturated are alkanes, unsaturated is alkene and alkynes. Double bond is alkene, triple bond is alkyl. So here the first and foremost thing which has been invented about the boiling point study was it is constant times with the Wiener index plus constant times with the polarity number and constant C. It's a linear relationship. Okay, obeying the rule. Okay, what is that Wiener index? It's one of the oldest topological index. It is simply the sum of the distance between all the vertices. Sum of the distance between all the vertices. So when you take the sum of the distance between all pair of vertices, there may be a repetition. So by divided by half. If you don't want this, we can follow the second formula that phi less than j, the distance between shortest distance between dA and bj. Take the shortest distance between v1, v2, v1, v3, v1, v4, v1, vn, and then with v2, with v3. So that's I running from 1 to n. Okay, so I can take either this formula or this one. So the most interesting things one to concentrate is the mathematician always interested about the small and big. Which is small, which is big, which is the lower bound, which is the upper bound. That is the immediate question a mathematician will have in mind. So if you take a graph, immediately you do any type of property study only on the trees. Only the trees. So if you take any tree, a tree is an acyclic connected graph. Take any tree, then the Wiener index of the path will be the largest. The Wiener index of the star will be the smallest. For the tree, because the path is a graph which is a long chain, goes directly. So distance between V1 and Vn is n minus 1. distance between V1 and Vn minus 1 is n minus 2, or V1, V2 is 1, V1, V3 is 2. The distance is increasing 1 plus 2 plus 3 plus 4 up to n minus 1. Then for the second vertex, the distance is 1 plus 2 plus 3 up to n minus 2. The third vertex, the distance is 1 plus 2 plus 3 up to n minus 3, and so on. So the distances are more when you add the sum of the distances. If you take the graph like a star graph, the distance between the center vertex to all other vertices is always 1. And the distance between all the pendant vertices in the star graph is 2. So this is the lower bound, this is the upper bound. Fine. So the number of widely used computational chemistry to measure some topological properties is study of quantitative structure properties. This is called QSPR, sorry, quantitative structure property relationship. Major area in computational chemistry. So topological indices are useful in the study of QSRP theory. Now let us consider a graph here. 4 vertices. We label V1 to V4 and calculate the Wiener index. The shortest distance between V1 and V2 is 1. V1, V3 is 2. V2, V3 is 1, and so on. And then the sum of the, I'm using the second formula, sum of the Wiener indices is, sum of the distances is 8. The index is 8 for this graph. Fine. So this graph is taken as an example for studying throughout this particular slides presentation. I am taking this graph to study. Structure is simple. And I don't know whether there is a compound, chemical compound in this structure. It took for me plenty of days to find a structure. I'll tell you when the structure has been displayed. So again, we try to explore the idea for a complete graph means connected everywhere the distance is 1. The answer Wiener index is n square minus n by 2 for a complete graph. For a path graph, it is the largest number n cube minus n by 6. For a star graph, it is n square. So again, the boundaries are there. For a given any graph, the lower bound is the complete graph, the upper bound is the path graph. So we will go to next concept, edge Wiener index. Edge Wiener index is the distance between, instead of vertices, carbon atom distance, we find the distance between the bonds, the covalent bonds or whatever be the bonds, but CC bonds. Distance between E1, E2 is 1, distance between E1, E3 is 2, E1, E5 is 2, E1, E4 is 3. So the Wiener index for this particular graph is given as 31, edge Wiener index. Can you convert this into line graph? Take all the edges to be vertices and draw the graph. This is called line graph of the graph T. And I can find the Wiener index of the graph. The Wiener index of the graph is nothing but this, what is say, edge Wiener index. So I can find the, for the line graph, W of T dash 16. And if T is a tree, we have a beautiful formula. Again, mathematicians are happy when you invent the formula. We feel always to go for connectivity without a definition. So here, edge Wiener index WE is nothing but 16. Edge Wiener is 16. That is equal to Wiener index minus NC2. So this is NC2 is the number. Here it's 15. So proper. Again, we people are interested in polynomial. Can you find a polynomial? Excuse me. So Wiener polynomial of a graph, the definition goes like this. It is sigma for all pair of vertices. Variable q, x is a variable or q is a variable. Q raised to the power d of uv. The shortest distance between uv, shortest distance uv, q raised per uv. So I can find what do you say, the distance, shortest distance between the vertices of this graph. Let us try to take this graph. shortest distance between V1, V2 is 1, V1, V3 is 2, V1, V4 is 3, V1, V5 is again, this is the shortest distance, 2, V1, V6 is 2, and V2, V6 is 1. V3, V6 is just 2, shortest distance, not going around like this. So in that way, we write out the, calculate the distances between all the vertices, even with the all V6 and V2 with the V6 and so on. Answer is 24. The Wiener index is 24. Well, so let us calculate the polynomial the Wiener index. How many pair of vertices are there of distance 1? How many pair of vertices are there of distance 1? So I think maybe I can interact with the participants, if any there. The participants can answer how many pair of vertices are there of distance 1?
There are 3.
How do you say 3?
V1, V2 having distance 1. V1,
No.
V6 is 1.
Okay.
Total distance. And V6 and V2 is 1.
So it's not 3, it's more than 3, no?
Yeah.
Even see V3, V4, V4, V5, V5, V6, V6. So how many pairs are there of distance 1? How many pairs of vertices will be there of distance 1? See,
7.
7. So what is 7 here? What is 7 here? When do you have an edge?
6.
When do you have an edge in a graph? When two vertices are connected by an edge, the distance between them is 1, right? So can I say that number of edges is the number of pairs? Can I say number of edges? Number of edges is 7 edges is here, right? There are 7 edges in this graph. So this 7q. 7q raised to the power of 1. 7q raised to the power of 1. Okay. Then how many pairs of edges are there of distance 2? Again, it is 7. So V1, V3, V2, V4, V3, V5, V4, V6, V3, V6, V1, V5, like that. So the 7 pair of vertices of distance 2. So 7 into q raised to the power 2. At last, there is only one distance 3. Distance 3, V1, V4. V1, V4, if you travel like this, or if you travel in this way, the distance is 3, both the sides. So there is only one pair, V1, V4, distance 3. So q raised to the power 3 is 1, coefficient is 1. So this is the Wiener polynomial, QQ plus 7Q square plus 7. Okay, I got the Wiener index 24. I got the Wiener polynomial. Now look at the calculus here playing the role. If I differentiate this Wiener polynomial with respect to the variable q, dw by dq, this is going to be 3q square plus 14q plus 7. 3q square 14. So now I got the derivative, first derivative. Let me substitute the value q equal to 1 here. I substitute q equal to 1 here, I get the answer 24, which is the Wiener index. So look at the beautiful calculation between the polynomial and Wiener. So I can obtain the Wiener index from the Wiener polynomial. That is the thing I want to convey to you. Interesting interplay between calculus and our whatever the structure and so on. Number index. The next improvement is that after 2000, that list I didn't add this. This is the new index in 2009. Now we are in 2023. Anyhow, my survey will go up to 2023. The distance-based molecular descriptor put by Ivan Gutman in 2009 is called terminal Wiener index. Instead of calculating the distances between all the vertices, calculate the distance between the pendant vertices. What is a pendant vertex? What is a pendant vertex?
Degree 1. Having degree 1.
Degree 1. All the vertices which are degree 1 is called pendant. How many pendant vertices are here? 1, 2, 3, 4, 5, 6 pendant vertices there. So I calculate the distance between only the pendant vertices, pair of pendant vertices, and then I calculate the distance between V1, V2, V1, V3, V1, V4, 5, V5, V6, then V2 with all and V3 with all. I get 51. So this is a new index called terminal Wiener index introduced by Gutmann, where he stated that why always we go with the calculation of the all carbon atoms, go with the carbon atoms which are pendant, that is CH3, methyl molecule part, the carbon atom which is carrying the end vertex, methyl. So it is easy to remove a person from the end, right? But it's a bit difficult to break a person in the middle. Suppose you have a human chain. You want to join the chain, you can join the chain at the end. You won't go break a person and join the chain in between. So this is the nature, right? So similarly, what he thought is in chemical compounds, attaching a new compound. So whenever I have two compounds in a test tube, have a reaction, maybe a fusion reaction or a combination, and then two compounds get mixed up, and then I get a third compound. It is easy that in the end you can attach the carbon. So that way, this idea was been used to find the terminal Wiener index. Ivan Gutmann is about 88 years old. He is in Serbia University. Still now he is the chief editor of the Math Communication newsletter. Of course, we have collaborated with the Gutmann with the two papers in the years, 2-3 years before. So he's a very active researcher, having PhD in mathematics as well as in chemistry. So such a personality has given terminal Wiener index. So we started working in terminal Wiener index for full binary tree, and then we calculated this particular along with our team for full binary tree with the levels, and the position. The formula comes out to be 2 raised to the power L minus 1, M is equal to 1 tail, M 2 power. Okay, this is available in the internet. So terminal Wiener index of graph G. Suppose G is a graph, and then I just add this CH3 C chain to all the carbon atoms, existing carbon atoms, V1, V2 up to Vn. Additionally, I add the methyl. CH3 is plugged. So this, as in graph terminology, it is called G plus graph. So G plus means add pendant vertices to all existing vertices. If that is the case, how to calculate the Wiener number? Again, we need not do the experiment, the compound, other thing, the lab test. It is all in the table. We just work out the calculation. WG plus is WG plus N into N minus 1. So this proof is available. You can just go through the proof on the internet. You can type the terminal Wiener index Bhaskar Babuji. You will get the results. Likewise, for a graph G plus X, we can find the terminal Wiener index. So we don't know whether C is going to be a lead compound. As a mathematician, we are designing the structure, and it is you, the pharmaceutical lab people, who are to go and find out whether such a type of compound is existing or not. So of course, the carbon atom valence is 4. I cannot think of a carbon atom with the valency 8 and 6 with the degree. So stable compound, unstable compound. Compound may be stable for some time and it will vanish. So for existing and a stable compound, which is going to be a medicine or drug or a dog, that is the invention they have to do. The mathematicians are giving a prediction. This is your range, this will be your index. If you want, you take it, otherwise you go for the next structure. So calculation purpose, mathematical format is 2p square minus 2p minus q for a given graph G plus X. G plus X means find out G and then add with X, with the new vertex X. And this is putting a long chain compound, long chain, maybe proteins, a long chain compound. A path graph is attached to a base graph G. So what is the terminal Wiener index? The formula has been worked out. And this is another play with the for terminal Wiener index with the original graph G with the K1 N, N. So number of K1, N star graphs are attached to this. Yeah. Then we have a theorem for caterpillar. You know what is a caterpillar? Caterpillar is graph in the path. We can have any number of pendant vertices per the vertices. So this is the result for caterpillar, and we have taken a terminal Wiener index study. It's a very old study, maybe in 2000. I don't remember the year. Before 2012. ABCD 4-position tetramethyl dopone. So this is the compound, and then we varied the positions of the methyl and studied the. These are the structures, and the compound we studied the terminal Wiener index. It's ranged from 91 to 100. So we were able to give a sequence of numbers. Given a compound, you find a number. Given a number, can you find a compound? It's called the reverse process. The reverse problem. If I give you a graph, I can find the Wiener index. But given a number, can you find a graph means it's a reverse problem. Yes, it has been true. It has been proved. But in the tree case, for this particular structure, we found that the sequence has arrived. So for the tetramethyl docoin, fine. So this is the terminal index for caterpillar graph. So I'll skip this. Then this is like a growing kata condensation dualist graph. This is the basic structure, like a Y structure, got from this particular deutersaturated tree T3. Every time it grows connected, deutersaturated tree for T30, T31, T32. The tree grows, and at the nth level, what is the index? So which level, what number, what size we require, we can do the work, and then we can stop the reaction at that stage. So for that, the calculation was useful. So the result goes like this. I am having less time, so I will bit rush up to the important concepts. The next speaker will join by 4 o'clock. So I will go to the important points to motivate you how this topological index is for drug designing. Likewise, I mentioned earlier, reverse Wiener index is a definition. Then reciprocal liver Wiener. So all these things are available in internet. Type the keyword, you'll get all the definition and concepts. Reciprocal reverse Wiener index, reciprocal complementary Wiener number, reciprocal complementary Wiener number. Then this is the butane graph, and the table we calculated for 2,2-dimethyl butane for various indices we calculated. And we studied that the relationship is like this. As I mentioned earlier, the energy of the graph is sum of the absolute value of the lambda eigenvalues. So this gives the energy of the graph. And yesterday index gives another index, topological indices. ZB Zagreb index will come in later stage. So what is the ultimate use is that to quantify the degree of folding long chain molecules, especially proteins, and this gives a measure for average centrality of complexity of the indices. So what is ZB? I have to say you what is ZB. ZB is Zagreb index. That is the next. Yeah, I will skip all these things. Yeah, this is Zagreb index. The sum of the squares of degrees of all the vertices Zagreb index. The product of the degrees of the adjacent vertices is called Zagreb index 2. M1 is Zagreb index. M2 is second Zagreb index. So this is the Zagreb index. First Zagreb index idea is 18. Second Zagreb index is 19. You remember the Wiener index was 8. Zagreb index is 18 here. So reformulate Zagreb index. This is the compound methyl cyclopropane. This one day when I was taking a class after the chemistry sir, he didn't erase the board. Then I copied from this board this compound. Then I went and searched the book. It was available engineering chemistry book, methylene cyclopropane. Such a beautiful, simple compound with the two double bonds very close. This is a stable compound. This compound gives me this particular graph which I took in the earlier picture. So this is very interesting methylene cyclopropane. It has a lot of properties and then predicted from the topological indices. Again, the interplay between the formulas, structures. So mathematicians are interested about the structure of the graphs, properties of the graphs, how the structure are there. Can we go for a structure equivalently in the chemical compounds in organic chemistry? This acid, COOH, benzoic acid, and its molecular formula graph is there, 42. So if you make structure very big, CN, and then with the pendant vertex, then how to calculate all those calculations. The most interesting thing is caterpillar 414 biregular. We arrived with the formula, and then with this formula, we tried to find out for all particle caterpillars. Okay, so and for the degree sequence, if I have a graph with the P vertices and Q edges, and then if there is at least one vertex of degree P minus 1, I can give the Wiener index. Without calculation, I can give the Wiener index P square minus P minus Q. This is possible only because one graph has delta P minus 1. Likewise, plenty of properties we can, in graph theory, can be studied in the chemical graphs also, and some properties are arrived from this. Well, I'll skip all those things. I'll go to the drug designing. This is a simple chemical reaction where I took this chemical reaction as a mathematical operation, and then all these things are available easily in open access. It is open access, you can see from internet. The application of the topological indices, the first application is about the recent, not recent, it is also old, maybe the HIV, human immunodeficiency virus, which causes damage. The anti-HIV therapy, you can postpone, that's all. The complete medicine is not there for diabetics or cancer or HIV. You can postpone your life at the end of your life, that's all. So how these drugs are designed, how our calculation is useful in designing the drugs. The anti-HIV therapy needs new drugs, which is being invented daily, because once a drug has to be invented, it takes a long time. It has to be tested. Okay, so to predict the anti-HIV activity of choline carboxylic acid using computational approach in topology. Okay, about the lab data. Okay, in Gupta et al. In 2012, he gave a model of predicting HIV of how active it is, this particular choline carboxylic acid. Okay, it was taken, the structure, and then various indices were being calculated for the structure, and the radical R is being moved here. Okay, so that we got about 60 structures like this, and calculated the linear index, W, terminal index, Zagreb Platt number, and we got positive, negative, which is active, inactive. Plus means active, minus means inactive, plus minus means active as inactive. So what is the range where it is inactive? In which range it was active? So that was the final what's the report. So where it is active, so many places it is active. It need not be active in all places. For a particular compound, some indices gives plus, some indices gives minus. So go for the average of that, and then they reported that about the range 2049 for Wiener index is active, and for terminal index it depends upon the pendant vertices. Hence, coalaxin carboxylic acid is transitional range. Zagreb index below 152, it was active. So this study helps people to go for a prediction and then work out to the lab experiment. See, automatically you won't get a lead compound. Trying many times, when suppose say you want to find the temperature, every time you cannot go near the furnace, the robot can go and find the temperature and come. Likewise, here mathematics helps as a tool. The graph theory helps as a tool for some prediction. The second case study was about cancer, marine ferridyl alkaloids. Again, this structure was taken, and then we calculated the indices, various indices, and then we got some assigned value in the lab and then reported value. And then we were able to publish some work, how our topological indices will be useful in the study of how active or inactive the anti-cancer drug activates with respect to Zagreb index and so on. Then coming to the recent COVID-19, again remdesivir, chloroquine, hydroxychloroquine, and theophylline. These were the things were treated. But today we have 3 booster injections. Still, a lot of people are going heart attack. Young people, they say that this is not worthy of having the injection, not having. So still things are going, but there are thousands of research paper and differential equation modeling came out, but nothing, it was under control. Everyone studied in a way, but we're not able to predict. We're not able to predict finally this is the way it will grow, it is the way it will happen tomorrow. So it is beyond the prediction, the nature has taken its shape. But in our study, to some extent, the novel coronavirus, beta coronavirus, shares a genetic sequence of viral structures. It is an urgent to identify the appropriate antiviral agent. Fine. So what we did in pharmaceutical drug design, the information related to physiochemical properties, biological activity molecular compounds are necessary. So we took, as usual, the topological index. In 2015, there was one a polynomial called class by class where this polynomial is a M of G is number of edges UV such that gamma U is I and gamma V is J into X power I, X power J. There are like your now Wiener polynomial, this is the M polynomial. It has 2 variables X and Y. where gamma u denotes the degree of vertices of the graph G. Then another neighborhood polynomial. Here we have again gamma n denote the neighborhood degree of sum of all edges, neighboring edges. So this is a polynomial for the particular graph structure. Degree based, it is degree based. So that from this we can calculate Zagreb index directly. Like Wiener polynomial to Wiener index, M polynomial to Zagreb index was calculated. So in 2020, Shovar Mandal and other discussed this paper, topological indices to some chemical structures. Okay, in this paper, a polycyclic aromatic compound, remdesivir. Okay, this is a nucleotide analog drug having broad spectrum activity developed to prevent the elbow virus infection. It is highly efficient to prevent 2019 COVID and so on. So this is the M polynomial which we calculated, and from this you substitute x is equal to 1, y is equal to 1. You are able to get the Zagreb index immediately for the income. So once you keep on changing the positions, the polynomial degrees will vary x square, y square. How many x square, y square degree is there? 2 degree is there. That is 9. How many x square, y per term is 4 is there. How many x cube, y cube? So all this calculation goes for the M polynomial. I will complete in 2-3 minutes. So this is the plotting graph. Using MATLAB, you can draw this graph for this M polynomial. Maybe cubic equations is very difficult, so MATLAB it is possible. And then the chloroquine. So hydroxychloroquine we added, we calculated for this polynomial and this particular indices. Okay, and then software. How software based approach for drug design. Today, software useful based on drug design to develop the models, major development in bioactivity compounds for the last 3 decades. Mainly, software is used to reduce the time and cost of the medicine. That is how the software is useful, and is a powerful tool for investigating the pharmaceutical lab properties of the drug. In addition, implementation of techniques could lead to reduce the cost of the drug and development. And in biomedicine sciences, these softwares are role of different phases of drug discovery. Okay, so this is how successfully drug discovery is going, and still we have to do a lot of things. Mathematicians has to further investigate and help the pharmaceutical lab people that better index is been found, and it will be friendly user to the pharmaceutical lab people to understand the physicochemical properties without testing, at least the range. Okay, this is the diagram for that computational software based. Okay, fine. And lastly, the software identification molecular accuracy of property. So this is employed to evaluate 1,000 molecules descriptor in a single stage. All the properties, electro-topological information theory based, can be calculated. So aligning a set of molecules of protein activities. Proteins are long chain with respect to co-crystal legend and developments. So these are the books which is available. This third book is copy is available nowadays in online. They can purchase Nande Trust Deck. First and second, I think in Institute of Mathematical Science, they have a copy. IIT Madras, I have taken it from Institute of Mathematical Science, Taramani. It's a very good book. It's not a print outside, not available. These are some referred papers of myself and my students. Good journals is the second journal, Math Communications in Mathematical Computational Chemistry. Ivan Gutman is the editor. Plenty of papers are available. It's a free access. Journal of Mathematical Chemistry is Springer. Discrete Applied Mathematics, okay, as you know, elsewhere. Discrete Mathematics is also not available for everyone, for few people. But you can directly open the site of Math Communication and look into papers. So any questions to encourage among ourselves? Otherwise, I thank all the participants who are patiently listening this particular FDP talk. Yeah, fine. I hand over to the organizers to organize for any questions. Participants. I think I finished in time. So I feel that to some extent I have tried to communicate for the youngsters to go through the internet and take some papers and they will read. Try to link spectral chemistry, a very big area, and computational chemistry. You can also take now the research in. You can write program and do, but still it's not. Mathematician won't go for a program. He wants to find a formula and then get out the good findings. Yeah, Karnagar sir. Please.
Okay, sir.
Any questions?
Thank you, sir.
Invite him.
Thank you, sir, for your lecture on topological indices of molecular graphs and drug design. This is the time for question and answer session. Because of huge participations and any particular who is interested to clarify his or her doubts, please come forward to post in Q&A box. Sir will clarify your doubts. Dear participants, if you have any doubts, please post in Q&A box. Sir will, otherwise you can unmute your mic and you can ask your doubts.
Good afternoon, sir.
Yeah, please.
My name is Dr. G. Jayalalitha from Wales University, Chennai, sir.
Yeah, already
Nice.
talked to me once. Yeah.
Nice
fine.
meeting you, sir. Your
Thank
presentation very nice. Can you suggest some books for the chemical graph theory, sir?
So I have posted 4 textbooks. No, that textbooks.
Okay, sir. Okay, didn't see properly that is why I think so. But,
no, you can. I'll send you the books. You can contact me. No problem. You can send me a mail. I'll send you the books.
Okay, sir. Because I'm doing in the chemical graph theory only.
Okay.
Based on the fractals only.
But nowadays they don't allow in Taramani to take full book Xerox. It's not all possible. Every chapter wise you got to go to take it. You can take it.
Okay,
I'll
sir,
get you. I'll let you know. Yeah.
Okay, sir. Thank you very much, sir. Thank you, sir. Thank you.
Good evening, sir. Sir, myself Tanya. I'm also pursuing my doctorate in
Okay.
Can you please share books with me as well? I really need those.
Not clear. Not clear. Please share.
Sir, Sir, can you please share those books with me as well? It will be very helpful for me.
Okay, fine. You can mail me. My mail ID is in the website. No, I'll reply to you. I'll text you. Yeah.
Thank you, sir.
Otherwise, I have to go back to the slide and put the slide again. That's what I have to do. But you can mail me. No problem. You can mail me. I'll give you. Any questions? Except books. Thank you.
Yes. Okay.
So if no more questions, I will thank sincerely the organizers of the Bapatla team, TSR and Karnakar and all other Sardi, all peoples which I remember. Acharya, my student and the head of the department. So convey my wishes to all the people whom I worked in Bapatla. Many more in future you arrange a lot of conferences and workshops and seminars to encourage the youngsters. All the best wishes. Thank you, and all. Thank you.
Thank you, sir. Thank you, one and all, for your good response and valuable support. Now, the second session is to be enriched with our lecture on graph labeling of the type magic, bi-magic, and anti-magic, given by our another resource person, Dr. D. Pratap Garu. Now, I request our staff organizers, Ms. K. Sunita, to present profound profile of Dr. D. Pratap Garu. Babji sir.
Good evening all. Welcome you all to a 5-day International Faculty Development Program on applications of mathematics in various fields with innovative approaches. I feel it as a privilege to introduce today's resource person, Dr. D. Pratap Garu. Dr. D. Pratap Garu is one of the senior associate professor working in the Department of Mathematics, CMR Institute of Technology, Bangalore. He did his MSc and MPhil in mathematics from Madras Christian College, Madras, and PhD from Acharya Nagarjuna University, Guntur, for the thesis entitled on contributions to graph labelings of type magic bimagic, and anti-magic. He has published 11 research papers in various reputed international journals and got 8 patents. He delivered invited talks in many national and international conferences. Presently, Dr. Pratap Garu is working in the area of graph labelings. Dr. D. Pratap Sir is appreciated by one and all with his best way of teaching for the last 3 decades. Moreover, his simplicity, teaching abilities, research capabilities, and good communication skills are an asset to him, in addition to his goodness and rich experience in the field of education.
Thank you, Ms. K. Sunita, for your nice introduction about Dr. D. Pratap Garu. Now I hand over the session to Dr. D. Pratap Garu. Dr. Pratap sir, please just start the session.
Okay. Yeah. Good evening, all. Are you able to hear my voice? Hello. Am I audible to you?
Yeah,
Sir,
yeah,
it
you're
is
audible.
it is audible, sir.
Yes, audible.
Sir, Pratap sir, please unmute your mic, sir. And share the screen, sir.
Yeah, I'll share it.
Okay.
Okay. Are you able to see me?
Sir, no problem.
Hello.
But the screen is not sharing, sir.
Yeah, 1 second. 1 second.
Okay, okay. It is audible also.
Yeah, I'll get back to you. 1 second.
Sign in అవుతున్నారు కదా.
Hello.
Sir, it is clear, sir.
Okay, fine. I hope I am audible and visible as well.
Yes, sir.
Yeah, first of all, I would like to thank all the organizers of this international faculty development program being held from 21st of this month. I'm really happy that Bapatla Engineering College Department of Mathematics has come up with an initiative like this, and very happy to be a part of this. I'm really, I feel blessed to be a part of this program because it is something like a very nostalgic moment for me, meeting my former colleagues, Dr. T. Srinivas Rao, Dr. P. Vijay Sardi, my dear friend Dayan Karnakar, Dr. K.V.L.N. Acharulu, and many others. Some of my students are there, I believe, Pothiraju and Sunita as well. So I'm happy to be a part of this. And in fact, I look forward to Bapatla Engineering College to conduct many such events, and then I wish to be a part of that also. Whenever you feel like you can incorporate me in any of those events, I'll be happy to come forward and support you all. I really thank even some of my other speakers of this FDP, like Dr. Bhaskar Babuji, my friend, and then Dr. Fanindra, and then other people. And I'm frankly speaking, I'm happy that I'm on par with these people on this platform sharing my talk. So coming to today's talk, I thank Ms. Sunita also for giving me a nice introduction about this. Coming to today's talk, Can you allow me to present my or share my screen? If you allow me to share my screen, I will do that.
1 minute, sir.
Yeah. Yeah.
Pratap Garu, you can present your screen now.
Yeah. Can you see this? Is it fine?
Yes, it's clear now.
Yes, sir. It is very clear and visible. Please go ahead, sir.
Yeah, okay. Thank you very much. So my today's talk is some graph labeling approaches, especially on magic, bimagic, and anti-magic. I am in fact privileged that my earlier speaker, one of my friends, Dr. Bhaskar Babuji, he has given a little introduction about the graph theory and some ideas about graph labelings and all that. So here, in fact, I'm happy to share that we together with myself and Dr. Babuji, we shared some papers, we presented some papers in some conferences on this Weynor index or Weynor number, and then even on labelings related to magic, bimagic, and all that. In fact, much of my research work, he has been an inspiration, and in fact, a lot of work, whatever I did, it is mainly because of him and his association with me. So I could do my research based on the concepts which he has developed and then his brainchild by magic labeling. So all that I did, and I'm happy that I am sharing the today's session also with him. So coming to today's thing, probably I think I was told to do my talk up to 4:45. I think I will try to complete within half an hour. And if possible, I'll try to use a writing pad also.
Sir, if possible, please take up to 5:15, sir.
Yeah, fine. I think you have a valedictory function also.
Yes, sir. So that will
I'll
be at
see
5:30.
what extent I could do. I will try.
Definitely, sir.
Okay.
Thank you, sir. Thank you very much, sir.
Yeah, fine. Yeah. Are you able to see the screen which I am able to write? Is that fine?
Yes, sir. Yes, sir.
So as and when required, I may be going back to this. So now for the time being, I'll go to this thing. Fine. So I'm not going much into the details of what is that, what is a graph and what is a labeling and all that. Maybe a few things, important things I will just touch upon and then go to my talk. Mostly in the recent past, what I have done is I try to engage some students who have been associated with me, accidentally, in fact. So I try to, like one of a student from a school. I do not know how he has come to know about my profile. He has come to me and he has requested so much, along with his parents, to do some kind of internship like thing on especially the graph labelings. I did not know how he got that interest and what is all that. But he came persistently and he requested me to give some kind of training on graph labelings. So it was a course that went on for 3-4 months as an internship. And then afterwards, during the course of our internship, we could develop some, what do you say, results, and we could arrive at some good results also. And then what we could do is we could establish certain bimagic labelings for certain graphs involving cycles. And in fact, I'm really surprised by the motivation of the student. And then together, I have incorporated his name. Together, we have published that in one of the recent journals. It got published also. So probably I am trying to explore the new challenges like this, where there is a scope from the regular what do you say, mode of research to encourage people who are actually interested in graph labelings. So when I asked him what was his motivation and all that, he has told that probably he has read somewhere in one of the write-ups about a conference being held on graph labelings, and then he happened to go through that article, just a few lines about it. I think I think my friend Bhaskar Babuji was also there, one of the speakers in that. And then he came and asked me, "Sir, I heard that you people have been involved in this. I'm really impressed by this idea of graph labeling. So you please give me some training on this." Now, the present status of that student is maybe he has in whatever work he has done along with me, he has put in his credentials and he applied some foreign university, and probably based on this interaction and then his work on the graph labelings, he has got an admission in one of the foreign universities. That is the status. Very recently I've come to know about this. So what I want to tell here is this is one of the potential topics that can help you to explore new areas, and then in fact will give you a right direction to, what do you say, to involve yourself in research and to come out with very important and interesting results. So this is a little history about graph labeling I want to give here. More than graph theory, graph labeling, somewhere in the mid 70s it has started. As you can see here, some 2-3 people, okay, I feel they are independently, they have come up with this kind of idea called graph labeling in the mid 1960s and 70s. So these people, what they have done is they try to introduce what is that, assigning numbers to these vertices and edges of a graph. So there, one of the important persons, Rosa, and then people like Graham and Sloan, they have done that. And then one of the first such labeling is called a beta valuation. And that is given like this. I hope you are able to see the diagram. This diagram given here will give you the details. The diagram given here, yeah, will give you the details. I hope this is visible to you now. Okay, so if you observe the diagram, what it says is the labelings are given only to vertices, but they are finding the difference of the absolute value difference between the adjacent labelings of the vertices. So all these edge labels are distinct. Okay, so that is if 0, 1, 2, 3, 4 are the labels given to vertices, and if you label the edges, with the number given by the absolute difference, then perhaps what you get, you are getting different numbers there. You can easily check for this given diagram, you get 4, 3, 2, 1, and so on. Okay, if you give them as labels to the edges. Okay, so there are certain things called based on this idea, several varieties of graph labelings have come up, and one such idea is even a graceful labeling. So maybe perhaps what I want to touch upon in today's talk is what are the different types of labelings that we have, and whichever is of interest to you, you can see in that. So if you talk about a graceful labeling, it is a graph with m edges having only its vertices labeled just like how I have shown in my diagram, and with some integers from 0 to k or something like that, such that no two vertices share the same length. So all these, there are variety of names given to labelings based on this idea of assigning numbers to the vertices and edges. In fact, many have come out of that, and my concentration is mainly on magic, bi-magic, and to anti-magic to an extent. So let me check with you what is, I'll just give an example of what it is. So people who are interested in these things, they can go ahead and continue with this. So suppose I'm giving you a simplest example so that the people who are new to graph theory can also follow this idea. Suppose I start with numbers like this. There are 3 vertices here, as you can see, and then there are 3 edges here. This is one edge, this is another edge, this is another edge. Suppose I label the vertices like this and the corresponding edges as, let us say, 4, 5, and 6. I'm giving you one of the simplest example. So here, with reference to this edge, suppose I make it as E1, edge 2, and edge 3. This is vertex V1, V2, and V3. So you can observe that if I take edge E1, what is the label of E1 and the label of the 2 vertices? What are they, V1 and V2? So if I take this, as you see, this is 6, this is 1, and this is 2, and the sum is nothing but 9. Similarly, if I take the edge 2, I think label of E2 plus label of V2 and the label of V3. So if you look at this, what do you get? 4 plus 2 plus 3. So this is equal to 9. Is that fine? So there is, similarly with respect to U3 also you can check this 5 plus 1 plus 3 again here. That will give you 9. So this we call it, this number, we call it a magic constant. Is it right? So in fact, when you talk in terms of particularly of labeling, this C3, what is this C3? Cycle with 3 vertices. Now, whenever it is a cycle and whenever it has n number of vertices, it will have the same number of edges as well. Okay, so C3 here, when I say cycle, it means it is a closed diagram like this. So edges are not. Okay, so all regular polygons, they come under this kind of this type of graphs called circles. Okay, so now what I do here is I say that this C3 here, because there are 3 vertices, C3 is a graph that admits a magic labeling. C3 is a graph that admits a magic labeling with a magic constant nine. Okay, so some people call it even edge magic labeling. These are all the different names that I have. I've given all that in my sliding. I can help you. When I go to the slides, I can tell you what it is. Okay, so now there is another name for this total edge magic labeling. The total here indicates that both the vertices and edges are labeled. Okay, so sometimes this total edge magic labeling is also mentioned as 1-1 edge magic labeling. So we are able to define edge magic labeling for a cycle C3. Okay, so similarly, if I make a little change to this, the vertices are like this. So this is V1, this is V2, this is V3. I said this is E1, this edge. The labeling given there is 1, 2, 3, and this is 6, this is 5, and this is 4. Now what I do is I just rotate or maybe shift the labeling. So instead of 1 being given here to the vertex, I give it to the edge. And then 2, instead of being given here to this vertex, I give it to this edge. And this label, I give it to this edge. And then the labels of the edges are being assigned to the vertices. So I get 5 here, 6 here, and 4 here. Okay, this is V1, this is V2, this is V3, this is E1, and this is E2, and this is E3. Now, what I do is with reference to each vertex, so I take this. So if I take vertex V1 and take the label of the vertex V1 plus the labels of the edges which are incident on this vertex, like a label of E1 and the label of E3. So what do I get here? I get this as 5 plus 1 plus 3, again 9. Is it right? So similarly, with reference to V2, I get the same thing. It is 6 plus 1 plus 2, again 9. So this, I call it, instead of edge magic, I call it vertex magic total labeling. Okay, I'm trying to give you the simplest of examples so that you can understand that very easily. Okay, so I say that C3 admits not just an edge by magic, sorry, not by magic, edge magic labeling. You can use any of these names, whatever I mentioned, edge magic or total edge magic or okay, 1-1 edge magic and all that. Okay, not just this alone, it also admits a vertex magic labeling. Okay, so whichever cycle is edge magic like this will also have a vertex magic labeling like this. Okay, so likewise, there are so many graphs or class of graphs or types of graphs which admit edge magic labeling and vertex magic labeling and all that. And my work was mostly based on not just identifying a magic labeling of type edge magic or magic labeling of type vertex magic. I just wanted to identify if there is not just a unique way of labeling, is there any other way of can we find more number of such labelings given a graph? So that was my study, and then my study has taken a more dimension, especially when I invested my time more on biomagic labeling. Because biomagic labeling means whenever there is only one magic constant, we call it uh, just magic labeling. If there are two magic constants, if there are two magic constants, such constants for a given graph, we call it edge biomagic and vertex biomagic labeling. We call them like this. Okay, so if you go back to this, I'll just show whatever I've done here. Yeah. Because I don't have much time, I'm just trying to go to the, yeah. So here, if you observe, I hope all of you know, yeah, certain basic terminology like KN, fan graph, wheel graph, and all that. Okay, so KN is magic. So whatever work is done, so by Stewart, okay, that is given here. Okay, Kn is magic and Kn comma n is also magic. Fan graphs are magic. Okay, whenever n is odd and all that. So this is what done. Wait. So these are all the different graphs that have been done, that have been given magic labeling. So we call super magic, super edge magic, super vertex magic. For example, a magic graph, we call it a super magic graph, or a edge magic graph, we call it super edge magic graph, if vertices are labeled from 1 to n. Okay, and similarly, a vertex magic graph, we call it a super vertex magic graph if the edges are labeled from 1 to n and the remaining vertices are labeled with the different numbers. So here, whenever we talk about magic or by magic graphs, the numbers that we assign, they are always from, if it is a cycle 1 to 2n, because if there are n vertices, there will be n edges. Isn't it? So if you use n numbers starting from 1 to n for the vertices, from n plus 1 to 2n, we will be using for edges. Okay, if it is a super vertex magic labeling, then what we do is, if we use 1 to n for the edges, then from n plus 1 to 2n, we will use it for the vertices. But anyway, what we are getting here is, if you take any in a super vertex magic labeling, what you get is, if you take a vertex and take the sum of the labels of that vertex and the edges incident on it, what we will be getting will be a constant. Okay, so that constant, we call it a magic constant. Okay, and then if you have two such numbers, we are calling them as biomagic labeling. So this is what we have a new variety of vertex magic. labeling. So a vertex magic total labeling is said to be V super vertex if F is from, I'm sorry, yeah. So the vertex set is labeled from 1, 2, 3, etc. V, and then a graph is called V super vertex if it admits a V super vertex magic labeling. So I told you earlier, whenever it is a super vertex magic labeling, what we said, edges will be labeled from 1 to n. Here, a new variety is introduced. Okay, so some these people, Vimal and Vijayalakshmi, they found some V super vertex magic labelings of some classes of parity graphs. Okay, and then we are coming up with odd vertex magic labeling, and then prime magic labeling. So all these things, see, a prime magic labeling is a magic labeling for which every label is a prime. So what we are trying to do is when we give only prime numbers, as labelings, then whatever, if we are able to arrive at a magic constant, we call it a magic labeling. So what are the graphs that can be identified having this magic labeling is always a challenge to the people who are interested to work on this. Okay, so this is the literature, whatever we have, whatever is available now. I'm just showing it here. So Becker and Hollander, they have showed that the smallest magic constant for a prime magic labeling is K4, 4, and that number is 114. Okay, so there are still people are, what do you say, obsessed with finding different types of words. See, we start with just magic labeling. Then we said what is edge magic and what is vertex magic. Once we know what is a vertex magic total labeling, we try to give some more kinds of labeling called V vertex magic, V super vertex magic total labeling, and all that. See, the prime idea, the main idea here is to identify uh, different types of graphs which have these labelings, and then identify different types of labelings for the different types of graphs, not just types of graphs, at least for a subclass can we find a labeling like this. So the idea here is, because of the vast applications that, I mean, in fact, my previous speaker, Dr. Babuji, he mentioned some of the applications, and he has discussed, in fact, in detail, especially, what do you say, chemical graph theory, and then molecular structures, and even in the drug usage, and then drug analysis also. So once we have this kind of labeling, so is there any connection for the labeling that we have generated and any applications that are there present? Because present day, everything people are trying to associate with some kind of study on coronavirus and the variants. So now even there is a team with which I am collaborating, where we are trying to find out the relationship between the labelings and the structures, or the, what do you say, whatever structures that we have there for different variants of coronavirus. Is there any connection that we are trying to explore that idea now? So not just coronavirus, you take different kinds of viruses. Now just because, I mean, the entire medical field and the biochemical field is much obsessed with this study on coronavirus. So people are doing more studies on that. So I hope whatever types of labelings that I have mentioned here, okay, if you can explore all that and then find out the kind of applications that I have told you where we can use that. We are still exploring where we can use the idea of labeling, and how the idea of labeling is going to be useful in the study or in the analysis of the structure and the symptoms of the different kinds of viruses that we have in our present day world. Okay, so this is another kind of labeling that we have. Vertex magic total labeling is said to be alpha vertex multiple magic. If the set of labels of vertices is a B edge multiple and B edge multiple magic, if the set of labels of the edges is given like this. So people who worked on this also I'm mentioning here. Maybe the number which I'm giving here will be able to, I think, because most of the people are interested to know where these ideas are available. So I've given a number here so that it is easy for you to refer. This number refers to the reference number given in the dynamic survey of graph labeling by Gallian. I think this number refers to the 2022 edition. So probably if I'm sharing this, my presentation with the organizers, those who are interested can go through this so that they can immediately access the papers that are given here. Okay, so I hope this will be helpful to you if I give like this. Now coming back to the edge magic total labeling and super edge magic, that is what I have given here. I told you already this. What is the edge magic total labeling and all that. Most of these graphs, whenever I try to give edge magic labeling or a super edge magic labeling or a vertex magic labeling or a super vertex magic labeling, I consider only simple graphs most of the time. I consider undirected graphs, and then I consider graphs which are connected. Okay, but I have also done in my research a little study on even directed graphs. Okay, and try to identify some of these varieties, if not the same labelings. Okay, so people recently, if you observe this, there is a labeling called reverse edge magic labeling. A reverse edge magic labeling with P vertices and Q edges is again a bijective function, such that, see, if you observe here, what you are doing is, if F, the sum of the vertices subtracted from the labels of the sum of the vertices subtracted from the label of the edge, if it gives a constant with reference to every edge, you're calling it reverse edge magic labeling. Okay, so the different types of labelings I'm presenting here so that you'll be able to go through them and you'll be able to identify where they would be used. So these are the people who found some new classes of reverse edge magic labeling here, Mr. Reddy and Sharaf Basha. Okay, and they have investigated a connection between the reverse edge magic labeling and different classes of other labelings. Okay, can I close in another 2 minutes? Is that fine? Organizers, is that fine? Can I take 2 more minutes?
So time is there, sir. You can continue.
Fine, fine. I'll try to complete as much as I could.
Okay, no problem.
Fine, fine. Yeah. So these are some of the edge magic total labelings. Sorry. Yeah. As I told you, the path graph also has edge magic total labelings for all n greater than or equal to 3. Okay, and they further proved that Kn also has an edge magic total labeling if and only if n equal to 1, 2, 3, 5 or 6. So these are the people who have given edge magic total labeling for complete graphs. They have also proved that paths, crowns, complete bipartite graphs, and cycles with a single edge attached to one vertex. Single edge attached to one vertex. I hope you have an idea to this? No, because on each type of labeling, we can spend, if we have a study on this, on each type of labeling, we can spend some hours so that we can identify certain graphs of this. So if this is your C3, what I do is I attach to edge to this. Okay, so this is the graph that they have been referring to, in fact. Okay. So cycles with a single edge attached to one vertex. So you're adding one more vertex and an edge, but they are pendant vertices. Is it right? So these people, Enomoto and Lado, Nakamigana, and then Ringel, proved that all the complete bipartite graphs are edge magic total. Okay, I think those people who have some knowledge of graph theory will be able to understand the different types of graphs that are being used here. Okay, so wheel graphs also. Wheel graph is nothing but, and again, a cycle. Maybe I'll just tell you. So if this is a cycle, C3, I introduce a new vertex and join this vertex to all other vertices. This I call it a wheel graph. Is that fine? So likewise, okay, so different types of graphs are there. I don't have much time to do for each and every one, but I think you can, when you refer to my presentation here, which I will be sharing with the organizers so that you can go through, you can find all these details. Okay. So we have this variety, super edge magic graphs, vertex magic total labeling. So they also have introduced the notion of vertex magic total labeling. Okay, so edge magic total labeling was given sometime in the 1980s, and then towards the end of the 20th century, we got this. What is that? Vertex magic total labeling defined by these people. Then the study has speeded up, and they could identify many such class of graphs which admit this kind of total labeling. So based on this, again, we have what are the different classes of graphs that have been given this labeling. That is mentioned here. K, M, and M plus 1 has a vertex magic total labeling for all M, and that K also has a vertex magic labeling. So these people like Miller, Slamin, and Wallis, they have given all those things. Let me just, yeah, this is, I just want to conclude with this. So the edge by magic total labeling, as I told you already, is defined by Bhaskar Babuji, and he has done a lot of work on this. And in fact, I also have worked on this, and then my entire research is based on this magic and by magic total labelings. So here, when he identified or when he introduced the by magic labeling, so he identified several graphs that have the edge by magic total labeling, and then what are the different types of graphs that have not just edge by magic total labeling, super edge by magic total labeling, and all that. Okay, so see here, there is one more alpha vertex consecutive edge by magic total labeling that is also given by Bhaskar Babuji along with his students Vishnu Priya and Jagadish. So this is alpha vertex consecutive edge by magic total as a graph, for which we have two positive integers K1 and K2. So as I told you, by magic means there will be two positive integers or two magic constants K1 and K2 given by this sum Fu plus Fv plus Fuv. Fu stands for vertex, label of a vertex U, Fv for label of a vertex V, and Fuv for the label of the edge connecting these two vertices. And whenever this sum is either K1 or K2, okay, for all the edges, and if the vertices are labeled by alpha plus 1, alpha plus 2, etc., alpha plus the absolute value of V, then, sorry, not the absolute value, the cardinality of V, this is what the by magic labeling that we get. Okay, so they proved that paths, and then star graphs, bi-star graphs, okay, trees, okay, they all can have this kind of total labeling. Alpha vertex, consecutive edge by magic total labeling. When we can add a pendant edge to a vertex adjacent to the end point of a path. So whenever you have a path, if to the end point of a path, if you can add a pendant edge, then perhaps we will be able to obtain this alpha vertex consecutive edge by magic total labeling. Okay, so these are all the different types of graph cycles, spans, wheel graphs, gear graphs. Okay, they all have been proved to be having alpha vertex consecutive edge by magic total labelings. And then some of the other types of graphs that are mentioned here, they also admit this alpha vertex consecutive edge by magic total labeling. Okay, so think I'll be stopping here. Okay, so if you have any queries, you please let me know so that I'll be able to clarify on them. I ask the officers to take over and let me know.
Pratap, can you hear me? Pratap?
Yes, sir. Yes.
See, one of your slide mentioned 16th or 17th slide, I don't know. Reverse super edge magic, right?
Yeah.
Introduced by Basha and Reddy.
Yeah.
The information given in J. Gallen is wrong. Basha and Reddy, they are making this from DAT, Vellore. But I spoke directly to Dr. DG Akka. DG Akka is in Tumkur, Karnataka. Retired professor from HMS Institute of Technology. He is the person who introduced this reverse in May 29, 2013.
Okay.
And the original paper is with me. I'll send you. And one of the co-author is Hunkund from Maharashtra, from a government college, Maharashtra. Akka is the guide and Hunkund is the student. I contacted the Tumkur people and then spoke to that Professor Akka. In 2000, after 2013, he didn't do any paper. It's a very good journal. He worked a discrete mathematics journal.
Yeah.
I will send you the paper to you.
Fine.
The information given by Basha and Reddy is not correct.
Yeah, I think we had a discussion on this a few months back.
Yes, so this is, exactly. So the reverse, the work is still, my student is now taking that working. Reverse edge magic, REM labeling, 2013 afterwards, they didn't work. So the Reddy and Sharif Basha, they are working plenty of work from DIT. But the data given in...
so originally it has been introduced by...
Akka.
Yeah.
From Karnataka, Akka.
Yeah.
Tumkur, and the student H.U.N.G. Hankund from Maharashtra.
Fine,
so that, I think if you do any paper, you put that...
I think in one of the conferences, if I remember correct, I met one of these people.
Okay. So that J. Gallen, we have to correct J. Gallen also. Send this paper to J. Gallen and then ask him to change the literature.
I think it's you have sent information to them regarding this, even to Gallian.
No, Galleon I didn't send, but I didn't have time to. But I inquired about Reddy and Sharif Pasha, what is happening in EIT Vellore. And then now I spoke to Gakka, so I said I will come with a new paper and contribute to his work. Yeah.
Fine. So that is a very good information, in fact. Yeah. So the correct people, they are not being recognized.
Exactly. That's what happening. Whoever sends information to Galen, he's very old age person. So Galen believes the people. Yeah. Should be. Yeah. Okay. Fine. Nice presentation.
Yeah. Thank you for that. Any other thing from other participants? I really thank all the participants for their patient hearing. I thank the organizers also. Now I request the organizers, if there is any query from the participants, to forward to me so that I can refer to that.
Okay, sir. Please wait, sir. Thank you, sir, for your lecture on graph labeling of the type magic, bimagic, and anti-magic. This is the time for question and answer session.
Yeah. I couldn't touch much on anti-magic introduced by Ringal. But if I had time, I could have done that also. But I thought that magic and bimagic for the time being, maybe we can reserve it for another topic or another discussion on another day.
Okay, sir. Dear participants, if you have any doubts, please post in Q&A box. Sir will clarify the same. Participants, any doubts? You can unmute your phone and you can ask. Ms. Varlakshmi, madam. Varlakshmi, madam. Please. Okay, right. Okay, Pratap ji. So, thank you one and all for your good response and valuable support. Now I request our co-convener, Dr. T. Srinivasrao Garu, to take it as an honor for saying special thanks to our today's resource persons on the behalf of Department of Mathematics, Bapatla Engineering College, Bapatla.
సార్ మ్యూట్ లో ఉన్నారు సార్ టిఎస్ఆర్ గారు అన్మ్యూట్ చేసుకుని మాట్లాడండి.
So good evening to all. On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource persons, Dr. J. Bhaskar Babuji Garu and Dr. D. Pratap Garu, for their valuable presentations. A huge challenge that medical scientists face today is the identification of compounds that are suitable for drug design. Graph theory is a fast-growing branch of mathematics, offers a natural way of relating compounds with their physical properties or their biological activity. I thank Dr. J. Bhaskar Babuji Garu for his presentation on topological indices of molecular graphs and drug design. Despite his busy work schedule in the university, he gladly accepted our invitation and gave a talk in today's session. Thank you very much, sir. Also, there are several types of graph labelings, namely vertex labeling, edge labeling, distance labeling, etc., that have real-life applications across various fields such as computer science, mathematics, physics, and social sciences. I thank Dr. D. Pratap Garu for his presentation on graph labelings of type, magic, bimagic, and anti-magic. In spite of his busy work schedule in the college, he cordially accepted our invitation and gave a talk in today's session. Thank you very much, sir. Today's sessions are really enriched with the presentations given by today's speakers on graph theory and its applications for exploring the knowledge in teaching community. This session has opened new ideas in faculty members for strengthening their research capabilities. Thank you.
Thank you, sir, for your special thanks to our resource persons. Now, this is the time for valedictory function. A very warm and healthy good evening to our principal, sir, Dr. Sheikh Nazir Garu, and the convener, head of the Department of Mathematics, Dr. Kevil Nacharli Garu, my dear colleagues and participants. Thank you one and all for your great support and a tremendous response for this 5-day International Faculty Development Program. All the 5 days are engaged with 7 different lectures by 7 eminent resource persons. Many participants are actively participated in all sessions and interacted with our resource persons to clarify their doubts. More importantly, all the resource persons are interested to greet this occasion with their valuable words. Now, this is the time for kind responses from our eminent resource persons through recorded videos.
Mathematics, Dr. Kevil and Acharya Garu, for giving me an opportunity to be a resource person for this workshop. I also thank
good evening, sir.
resource persons
Not here.
efforts to make this workshop a success. And in fact, I thank the participants. In fact, the overwhelming response from the participants who have participated from all the corners of the country. Abhila, this is my first experience of being a resource person to such a kind of workshop in which participants were there from north to south and east to west of India. I really appreciate your enthusiasm and interest in the workshop. In fact, a couple of participants in my lecture also have enthusiastically shown response and fired a few questions. I thank all of you, and I thank one and all for giving me this opportunity. Thank you, one and all.
Good evening, respected dignitaries of the dais and respected participants. I am Dr. K. Prasad, Senior Assistant Professor, Department of Mathematics, Guru Kashdas Vishwavidyalaya, Bilaspur, Chhattisgarh, India. On the occasion of 103 birth anniversary celebrations of a great mathematician, Professor K. Chandrasekharan sir, Department of Mathematics, Bapatla Engineering College organized a 5-day International Faculty Development Program on applications of mathematics in various fields with innovative approaches from 21st November to 25th November 2023 through virtual mode 4 to 6 p.m. I congratulations to convener of this program, Dr. Kevalan Acharya Garu and his team for successfully conducted this event. I am taking this opportunity for express my sincere gratitude and thanks also for choosing me as a resource person in this great event. I give a lecture on the problem of discontinued to fixed points on the second day. I hope that in future also, Department of Mathematics may conduct such type of programs also. This type of programs may be useful for new researchers and faculty members also. Once again, I congratulate to the organizing committee and his team for successfully conducting of this event. Thank you very much.
Dear participants and organizing committee members, I am very happy to be a resource person for this International Faculty Development Program. I really enjoyed a lot the response from the participants. It's not easy to conduct a faculty development program without proper planning and timely executions. When I received a phone call from the Kevalan Acharya Garu, I accepted his invitation immediately because of his long association with him, more than 20 years. We both of us did our PhD under guidance of Professor N.C.S. Pattabhiramacharya. He is a retired professor from NIT Warangal. I also appreciate the entire teamwork, Kevalan Acharya Garu, T. Srinivas Rao Garu, and Karunakar Garu, and some other faculty members from the department. Special thanks to Principal Sir. This is a good program. This kind of variation for the benefit of the department. And I think every faculty member got benefited by attending this kind of program. The teamwork under guidance of Dr. Acharya will definitely help the department for strengthening in so many aspects. Wishing you all the best.
First of all, let me introduce myself as alumni of Bapatla College. I learned many things from this college and my career was strong foundation. I am thankful to the convener and principal sir for giving me this opportunity as a resource person. The International Faculty Development Program, AMBLIA. Myself and Dr. Kevalan Acharya Garu did collaborative research work and published many research papers with the blessings of our Professor N.C.S. Pattabhiramacharya. Here I am telling special wishes to the organizing team, Dr. T. Srinivas Rao sir, Sri Karunakar sir, Ms. Rajeshwari madam, and Ms. K. Sunita madam for their teamwork and sincere efforts for completing the everyone. And special thanks to Principal sir and college management to encourage the faculty members for conducting useful programs to teaching community. Finally, all the best to all the participants who attended this FDP for enriching their knowledge. Thank you all and all.
Department of Mathematics for organizing the International Faculty Development Program on the campus in virtual mode. And it is very thoughtful of all the faculty in the department to celebrate the birth anniversary, 103rd birth anniversary of the legendary mathematician Kovaruvala Chandrasekhar Garu. The conference sessions are on various areas in mathematics, are all well organized with a nice coordination among the faculty. I am happy to be associated with the conference, and I thank the organizers for giving me this opportunity.
Bapatla Engineering College is one of the best technical institutes in Andhra Pradesh. I feel proud to be a team member of the FDP program as a resource person. I thank sincerely the organizing committee for arranging such a wonderful program. I don't forget Bapatla Engineering College, which has uplifted my career
I congratulate the organizing committee and management of Bapatla Engineering College. My best wishes to all the participants.
Hello everyone, I'm Pratap Dayadi from CMR Institute of Technology and one of the resource persons for the online 5-day International Faculty Development Program on the applications of mathematics in various fields with innovative approaches being held from 21st to 25th November 2023. First of all, I congratulate all the team of organizers, Dr. KVLN Acharyalu, the convener of the FDP, Dr. T. Srinivas Rao, the co-convener of the FDP, and Sri N. Karnakar, the staff coordinator of this FDP, and the other staff organizers. I'm really happy that I'm a part of it, and then it is something like a reunion for me. I'm meeting my former colleagues and being a part of this FDP. Really, I give all my support and best wishes to this particular department and to this particular events like this, which are being organized from Bapatla Engineering College. I'm really happy that you people have come up with an initiative to do this kind of faculty development programs and other programs. So I'm very happy, and then I really look forward to being a part of all those events which you are conducting or you're going to conduct. I wish the best of everything for you in all your endeavors. Thank you so much for giving me this opportunity. Thank you.
We are all thankful to them for spending their precious time to deliver their beneficial lectures and also sending their valuable responses. Now I request our convener and head of the Department of Mathematics, Bapatla Engineering College, Dr. KVLN Acharyalu Garu, to give his message.
Good evening to all. I extend a warm and heartfelt welcome to our beloved principal, sir, Dr. Sheikh Najir Garu, my respected and eminent teachers, Dr. Bhaskar Babuji Garu, Dr. Pratap Garu, and dear esteemed faculty members. We gather here today through online to participate in this valedictory function of our International Faculty Development Program. It is with a great pleasure and a sense of accomplishment that I came here before you to deliver my convener's message on this auspicious occasion. First of all, let me express my special thanks to today's resource persons, Dr. Bhaskar Babuji sir and Dr. Pratap sir, for their innovative talks. Both are well experienced and eminent teachers. They inspired many students for the last 3 decades. Moreover, both are accomplished notable achievements in teaching as well as in the research field. In view of birthday anniversary celebrations of Dr. Komaruvolu Chandrasekhar Garu from 21st November to 5th November 2023, can you hear, sir? I think here we have some power problem.
It is audible,
yes,
sir.
Sir, your voice is clear, sir.
Very good. It is enough, sir. So, in the view of birthday anniversary celebrations of Dr. Komaruvolu Chandrasekhar Garu from 21st November to 25th November 2023, we have successfully conducted this international FDP with the enlightening lectures given by our revered resource persons, Dr. N. Sudhakar Garu, Dr. KNVV Varaprasad Garu, Dr. CV Pavan Kumar Garu, Dr. N. Fanikumar Garu, Dr. P. Anuradha Kameshwari Garu, Dr. J. Bhaskar Babuji Garu, Dr. D. Pratap Garu. With this FDP's journey of growth, learning and collaboration which cultivates a spirit of continuous improvement with acquiring new knowledge. I am very happy to inform you that huge number of participants registered throughout India, and most of them stayed with us till the completion of all sessions in every day. I am thankful to all the participants for their interest to extend their FDP and made it as a good platform for professional growth and continuous improvement in innovative teaching methodologies. When we put a proposal for conducting this international FDP to our beloved principal, sir, Dr. Sheikh Najir Garu, that minute onwards, our Principal sir has been giving his valuable support, marvelous encouragement, and timely cooperation to us for conducting this FDP in an effective manner. Thank you, sir. Thank you very much for your cooperation. In particular, we are all thankful to our magnanimous management for their constant support and encouragement for conducting useful programs for faculty members as well as students in view of enhancing the knowledge with emerging trends in education. You all know that these types of programs can be succeeded only with teamwork, seamless coordination, meticulous planning, and collective efforts. Our co-convener, Dr. T. Srinivas Rao Garu, has truly made this international FDP a successful one with his good efforts along with the cooperation of coordinator Sri N. Karunakar Garu, staff organizers Ms. I. Rajeshwari Madam, Ms. K. Sunita Madam, and along with other faculty members of our department. Dr. K. Manideep Garu from CSC department, Sri A. Sai Kishore Garu, Sri U. Venugopal Garu, and MCHOD Sri N. Kiran Kumar Garu extended their timely technical support to us for making this event a successful one. The aim of this program is fulfilled and became a fruitful one only because of our esteemed participants. I express my sincere appreciation to each and every participant for their active participation and valuable cooperation for all sessions to make this program a grand success. Expecting the same response from the participants in our future endeavors also. Thank you, one and all.
Thank you, sir, for your valuable message. Now I request our principal, Dr. Nazir Sheikh Garu, to give his message.
Najir sir, please unmute, sir. Unmute your audio, sir, please.
Now, is it audible, sir?
Yes, sir. Yes, sir.
Okay. Today's our resource persons, Dr. J. Bhaskar Babuchi Garu from Anna University and Dr. D. Pratap Garu, Associate Professor, CMRIT. Sir, good evening, sir. And our other faculty participants, Mathematics Head of the Department, Dr. K. Veeran Acharya Garu, our Senior Faculty Member, Dr. T. Srinivas Rao Garu, other colleagues, Karunakar Garu, and all faculty participants, very good evening to all, sir. Really, today we are very happy, sir, in our campus. So almost there are so many activities are going on. One side, Department of Mathematics is conducting the valedictory last Monday to till today. So eminent resource person, they are sharing their knowledge to all the researchers, faculty, fraternity. Definitely, this is a wonderful program. I hope all the participants enjoyed last 5 days with so much useful information regarding their teaching learning process as well as research perspective. And today I'm very happy to see our Pratap sir after a long time. Sir, really, we are happy to see you, sir, after a long time.
Yes, sir, I am also very happy.
Really, I'm great to see you, sir. And Bapuji, sir, also sharing this platform and giving the all your sharing the knowledge to all our participants. Sir. Thank you, sir. Thank you very much. Even your very busy schedule, also you accepted our invitation and sharing your knowledge, sir. And last 1 week, so all the eminent research. So I congratulate to Department of Mathematics, Head of the Department, and entire team of Mathematics. Really, they organized, conducted, and successfully completed international faculty development programs. Really, it's a very useful program conducting by the Department of Mathematics. Really, I'm happy to say that every day, not less than 230, 250 participants are participating. It's a very rare occasion in the recent faculty development programs, what we observed even in engineering faculty development programs also. So really, thanks to all the participants. So every day, for all the resource persons, what they are delivering so keenly, they are attending the workshop, faculty development program, and question answer session also very active in last 5 days also. Thanks to all the resource persons from last 5 days and today's 2 resource persons also. And today we completed utter faculty development program in offline mode also. There also really a very good applause, and eminent resource persons came and they delivered outcome-based education in the campus. All the heads of the department, in their perspective, they are conducting various research as well as academic programs. Really, we are very happy. From on behalf of Bapatla Engineering College, I thanks to all the heads of the department and all the resource persons taking their time and associating to Bapatla Engineering College and sharing the knowledge. And really, we all faculty fraternity, thanks to all the resource persons. I congratulate once again to Dr. K. Viran Acharya Garu and his team for successfully, in a grand way, completed this faculty development program. Really a wonderful program conducted by you and your team, sir. Thank you very much, sir. Thank you, one and all. Thank you, sir.
Thank you very much, sir, for your inspiring speech. Now I request one of our senior faculty members and Professor Dr. P. Vijay Garu to address the gathering on this memorable day.
So, good evening all. Beloved Principal Dr. Sheikh Nazir Garu, respected HOD of Mathematics Department Dr. Kevilan Acharya Garu, esteemed organizers of the Faculty Development Program, active participants of this FDP, a very good evening to all. We all came together here for the valedictory function of our International Faculty Development Program on applications of mathematics in various fields with innovative approaches. As a part of 150th birth anniversary of mathematics legend, Sri Komaruvolu Chandrasekharan Garu, as one of the senior member of the department, I am deeply impressed by the dedication and enthusiasm shown by each participant throughout this transformative journey. Our commitment to excel in mathematics education and its application has been reaffirmed through this program. We have explored advanced mathematical concepts and embraced the latest technologies to enhance our teaching methods. The exchange of ideas and the collaborative spirit among us have been truly inspiring and creating a vibrant atmosphere of intellectual growth. I extend my sincere appreciation to the organizers, facilitators, and all participants who have contributed to the success of this program. The collective effort and passion for advancing in mathematical education, along with its applications with our department, are commendable. The success of this faculty development program is a result of the combined effort of the following: the great support of our management members, advanced and informative lectures in multifarious fields of mathematics, along with applications delivered by the eminent resource persons from national and international institutions. Valuable guidance of our dynamic principal, Dr. Nazir Sheikh Garu, meticulous planning and great vision of our head of the department, Dr. Kevilan Acharya Garu, proper execution and sincere efforts put by our co-convener Dr. Srinivas Rao Garu and his team members, Sri N. Karunakar Garu and Ms. K. Sunita. And last but not least, the cooperation extended by all our faculty of mathematics department. As a next step in this direction, let us carry out the spirit of continuous learning and collaboration into our classrooms. The knowledge gained during the FDP may serve as a catalyst for further innovation and excellence in the field of mathematics education and its applications. Congratulations to each and every one of you on the successful completion of this program. Let us continue our journey in mathematics education with a thirst for knowledge, a commitment to excellence, and a shared passion for inspiring the next generation of mathematicians. Thank you, one and all, for giving me this opportunity.
Thank you very much, sir, for your speech. It is the time to know the responses from our participants. I request the participants, please give your valuable opinions about this International Faculty Development Program, applications of mathematics in various fields with innovative approaches. First one, I want to request Dr. NCH Ramgopal Garu, Associate Professor, MLR Institute of Technology, Dindigal, Hyderabad, to give your opinion on this FDP.
Good evening, sir. Am I audible to you?
Yes, sir, you are audible.
Yeah, thank you very much, sir. Good evening, all. Myself, Dr. NCH NCH Ramgopal from MLR Institute of Technology, Hyderabad. First of all, I would like to congratulate the department of Bapatla, Mathematics Department of Bapatla Engineering College for conducting such an useful faculty development program, and also great appreciations to the management of Bapatla Engineering College as well as the principal of Bapatla Engineering College for supporting such an excellent program. And I can say one thing, sir. All the sessions from last 5 days exactly match with the title, Innovative Approaches. That's really excellent, and it is very useful for the young researchers. And many of the sessions, all the sessions are very interesting. And particularly today's session, the collaborative work with mathematics and chemistry. Yeah, that's encouraging, and request you to conduct such programs in future also, even offline mode also. Definitely, we all will support. And in interdisciplinary research, particularly concentrating on interdisciplinary research, mathematics and electronics, mathematics and computer science, like that, because everybody knows that mathematics, without mathematics, there is no other subject that we can say. So I really appreciate once again, and thank you very much, sir.
Thank you very much, sir. Now I request Dr. R. Krishna Kumar Garu, Assistant Professor, Career Development Center, SR Minister of Science and Technology, to express your valuable response. Krishna Kumari Garu. Krishna Kumari Garu. Madam, are you available? Now I request S. Veeresh, Assistant Professor, Sri Vasavi Engineering College, Tadepalli Gudam, to express your opinion on your FDP program. Veeresh, Sir Veeresh. Now I request Divya Suresh, Assistant Professor, Department of Mathematics, Sri Buddha College of Engineering, Pattur, to express your response on our FDP program. Now I request Arun Gosep, Assistant Professor, Department of Mathematics, SR Minister of Science and Technology, to express your opinion on our FDP. Okay. Now I request Saroja Sethi, Department of Mathematics, HKE Societies SLN College of Engineering. Okay, sir. Today's session concludes with a vote of thanks by our co-convener, Dr. T. Srinivas Rao Garu.
Respected Principal Dr. Najir Sheikh Garu, our beloved HOD, Dr. K.V.L. Nacharlu Garu, honorable resource persons, my dear fellow faculty members and participants, a good evening to all. It's my privilege to propose the vote of thanks to all who have helped us in making this FDP such a resounding success. First of all, I would like to express my sincere thanks to our management and principal sir for their encouragement and providing us all the necessary facilities for conducting this FDP smoothly and successfully. I would like to thank our distinguished speakers, Dr. N. Sudhakar Garu, Dr. P. Anuradha Kameswari Garu, Dr. J. Bhaskar Bapuji Garu, Dr. K. N. V. Varaprasad Garu, Dr. N. Fanikumar Garu, Dr. C. V. Pavan Kumar Garu, Dr. D. Pratap Garu for giving excellent presentations and making this FDP so interesting and meaningful. I would like to thank our beloved head of the department, Dr. K.V.L. Nacharlu Garu, for his constant support and guidance throughout this FDP. I am happy to express my sincere thanks to our faculty members who have made this FDP a grand success with their cooperation in all the aspects. I would like to thank Sri N. Kiran Kumar Garu, HOD of MCA, Dr. K. Mandeep Garu, faculty of CSE department, Sri A. Sai Kishore Garu and Sri U. Venugopal Garu, who extended their technical support in conducting this FDP smoothly. Last but not least, I thank all the participants who have turned up in such a great number from different institutions across the country for attending this FDP. Thank you, one and all.
Thank you, sir. Thank you very much.
Thank you very much.
Thank you, sir.
So today's feedback link will be shared. Today's feedback link will be shared in WhatsApp groups. Please fill it and share it to us.
Okay, bye.
Okay, sir.
Bye,
sir.
bye,
Bye,
sir.
sir.
Thank you very much.
Thank you, sir. Thank you
Thank
very
you.
much.
Thank you. Thank you. Thank you.
See you all. Bye.